more set of. So yesterday we did a simple toy model for the free energy, right? Then we went to a real alloy, which was aluminum zinc and did dendritic growth. Then we did a eutectic, which is a multi-phase situation. So today we'll do a ternary and then a totally multi-component system first. And then we'll try to, as a homework or a class work, try to create a system totally of the new. So for example, a peritectic reaction that we will try to do ourselves. Okay, so I'll give you a task. We'll use the function f1 and try to create a peritectic system. All right, so that's the idea. So let's go into the examples quickly. So we'll import infile as we were doing before. You all know this. Go to the sys folder that he shared with you yesterday. And what we will try to simulate is, for example, a ternary system. So let's do an NiAl chromium system. Okay. So you will see over here there's something called. So no, let's not do this system because the thing is missing. Let's do NiLMO. Okay, just go to NiLMO folder and you will find these files there inside. Okay, so click on NiLMO 4.in, and again this will tell these things. Don't worry about it. Okay. So remember there is a ternary alloy. So in contrast to what you had before, you are now going to have two components that you're going to be solving for. All right. So that's what you will see when you essentially input the components. So we'll make it slightly larger, 200 cross 200. Okay. Dimension stays 2. So these are now in real units. So that's why you see 3 minus 8 meters as the length scale and some time step that allows you to run stably. All right. So you see over here there are 2 phases and 3 components. Okay. So here aluminium, moly and nickel. So essentially we are going to be solving for aluminium and moly, and nickel essentially is a dependent variable. So one component is essentially something that is next. So this is remaining the same. We are going to be solving for not 2 lakh, 20,000 steps and storing at 1,000. Next. And now you see the difference in the diffusivity. Instead of one value, now you have supposed to be entering 2 values. Okay, because it is a ternary alloy. So the diffusivity matrix or interdiffusivity matrix is 2 cross 2. All right. If I use a diagonal matrix, I have to enter only these 2 values. However, if I choose a full matrix, you see the other values also get to be initialized. So for example, I will, here it is a one-sided model. So that's why what you see over here, if I choose diagonal matrix, 0, 0 is selected because alpha is the solid. Okay. If you look at the liquid phase, you see 1 E minus 9 and 0.5 E minus 9 as the diagonal elements. So you essentially have that D11 and D22 are different and they are taking these values. All right. Everybody here until this point? You're able to load and do it? Okay. And eigenstrain and elastic constants are to be used only if you essentially have an elasticity problem to be solved. Gamma, you have only one interface, so 0.1. And functional properties is something that I will allude to today because yesterday I did not spend too much time here. Remember, we are solving a real alloy and we are using the thermodynamic description F is equal to 4, because one of the descriptions I told you during the thermodynamic coupling class. Now, in this description, we read the CSV files which I had showed you yesterday. What you have to do for doing that is to associate the alpha and liquid phases with the real thermodynamic phases. Okay, so the real thermodynamic phases are FCC-A1 and liquid. Okay, so you have to say that alpha is associated with FCC-A1 and the beta is associated with the liquid phase, such that the alpha's thermodynamic information gets derived out of the relevant thermodynamic files that you are putting in the TDB's encrypted folder. All right. So this is what the phase map is telling. The phase map essentially maps the proxy phases that you have in the system, alpha and liquid, to the real thermodynamic phases, FCC-A1 and liquid. Okay, it's a one-to-one mapping. So let's say now you have multiple grains, alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, and then liquid. But each of the alphas have the same thermodynamics. The map could look like this: FCC-A1, 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 comma liquid, which would associate each of the alphas to the same thermodynamic information that you have over here. So it's a phase map. All right, this has to be provided, otherwise you don't have the associated thermodynamic information. So the thermophases are essentially telling how many distinct thermodynamic phases are you inputting into your folder. Here we have 2, so we are inputting 2. So phase composition properties are exactly the same, except what you now see is that you are now inputting 2 values over here instead of 1 value before for each phase, because it's a ternary alloy. You have to input 2 components. So your component, this is the aluminium composition, this is the moly composition as the equilibrium, and this is essentially derived from the same file that I showed you yesterday, that the equilibrium at a given temperature is what I am initializing, and C-fill is essentially the filling composition at the equilibrium if I am giving my driving force with the undercooling. If I am giving my driving force using a supersaturation, then my temperature will be the same equilibrium temperature, and I have filled the composition different from the equilibrium. Okay, that way you can give supersaturation. And I am again giving a rotated anisotropy, which is at 45 degrees. So all of this you know, so let's go ahead. Let's fill a solid, which is, let's say, a cylinder at the corner. And let's add another cylinder maybe. Or maybe, yeah, let's add another cylinder. At the center of the domain. And then go next. Okay. So next. So now you see the simulation type is ternary because we are doing a component system. All right. And this is a field I'm using such that I don't again invoke the matrix inversion in a way that is the typical matrix inversion. I hand code the matrix inversion because for a ternary system you can work it out what the matrix inversion is and code it in. So we call the matrix inversion routine generic for a multi-component system here that allows you to do a quick simulation. So this, all of it you know. Here again I am using function anisotropy 1, which means the anisotropy is switched on with 4th type anisotropy, and DAB is equal to 0.1, so 1% anisotropy. Okay, so the function W is 1 and the equilibrium temperature is 1590. I'm filling it with 1580, so 10 degree undercooling, and that is what we'll be using. Okay, 10 Kelvin undercooling. There's some small noise of 0.1 amplitude, and so let's go next. So we are doing this today. So this is our 6th in file. So we'll create this. Okay, and let's do this. Generate in files. Same place that you read the in files from. Just choose that same place. You should get this. And since all of you have the running thing, so just click run. So now you can see here that in this running thing, you have alpha and liquid, but now you have 2 components being executed, one for the aluminium, another for the moly. Okay, because you're solving for two components, right? In contrast to one that you had before for the binary. All of you are able to get until here? Then what is the issue with that? Okay. Running for everybody? Okay. So for me it has executed. So I will go up and I will do as I was doing yesterday. I'll check what will happen in the data. So the files have been created. Okay, so it should be able to do this. And then we'll go into the data folder and view the files. These XMF files would have got created here, which you can now view. So you should get a revolution like this. Again, because it's 45 degree rotated, it's rotated like that. This guy will want to grow as a corner, like this, and this guy wanting to grow here. So let me know when you reach this stage. He has it, no, say he is using singularity, no? Singularity में पहला view has. All of you are able to get? Ankush? Okay, so here is what the composition looks like. So there are two compositions now, aluminium and moly, which is what you get over here, right? And you can check for the two chemical potentials, aluminium and moly. Okay. Huh?
It's not a day.
What is?
The chemical potential is not constant.
Yeah, it's not uniform because and therefore it's growing. Are you able to get until this point? Okay. And take a plotter line and plot the compositions. And you see that the compositions are behaving differently. Okay. You see the compositions are of different types. The value of the moly is very different from how the aluminium is in the system. Okay, they are evolving differently. Aluminium is almost very small composition gradient, whereas the moly has a larger composition gradient. And that can happen because of the initial phase diagram where you are, the initial tie line, as well as the diffusivity is being given. Okay, so this is where you how you do the XMF conversion. You type this command. This is the XTMF where your XTMF is. So just do tilde slash microsim slash GR grand tab, write XDMF, the input file that you are using, and the output file, the prefix of the output file for the timestamps, and start and the end timestamps. Okay, so Running for all of you. We are back to the stage where we are yesterday. So the next step we'll be doing is a 5-component system. Okay, so this is a real IN718 system which we will try to simulate. All right. So let's go back over here and import a file. Choose in file and go here. And there is something called IN7. Well, this is supposed to be 718. It's INZ18. Okay. Just open this, and you would find several of these things inside. Arun, this is input.in or input TDB IN718. This one. Huh? So just select this, and that's it will look like this. INZ18. Okay. What is the issue with that? All right. So if you have come here, then what you do is most of these things, as you will see, is similar. This is also a real system, so you will see these parameters. But here you will see number of phases 2, number of components 10. Okay, so we are trying to really do a IN718 system. All right. So you can see the name of the components as well: silicon, cobalt, titanium, chromium, manganese, iron, aluminium, niobium, moly. Okay. 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 This has hung somehow, so we will just reopen this. Just 1 second, my system hanged for some reason. So. Okay. What is that? Get 10, no? Number of components are 10, no? Yeah, 10 means 9. So we'll input 9. Okay, so here we will run slightly different, 40,000, save at 1,000. All of these are the same. And as you see, now it's a full-fledged diffusivity matrix. Okay, you see, you can enter. If it's a diagonal matrix, you need to enter only these values. All right, but if it is not, you have to enter the entire thing, okay, which looks chaotic because space is very small. All right. So, but we will stick to diagonal matrix so that we can enter these values. One is solid, so all of these values are 0. The other one is liquid, so all of these values are 3 minus 9. Okay, presently all are equal. Okay, so let's go to gamma. You can put gamma 1, 2, which is only one interface present. So solid and liquid. So here everything else will be same. We are putting a surface solid interfacial energy of 0.1, but functional properties we will use same 4. Don't worry about this. We have FCC and liquid as the two thermodynamic phases, which is mapped like this. Okay. Phase compositions, as you will see, you have to input 9 components now. So this is a long vector, right? So if you go here, you can see all the 9 components, which we will not worry about now. And you have a rotation of 0, 0, which means the anisotropy is oriented in this direction. All right. So you have 0, 0, 1 in the growth. So what we will do is to have periodic boundary conditions for this boundary as well as the x minus boundary. Whereas for the Neumann, for the y plus and y minus, we will have Neumann boundary condition. This is typical for directional conditions as we have seen for the utility. All right. And then we fill. So we will import a filling file because Arun has already written one. As we showed yesterday, you can import a file for filling as well. So go here from the same place that you imported the thermodynamic file. Basically go here in this folder and import filling.in. Okay, so it will fill some Q. Okay, come to this stage quickly. Okay, so once you have done that, do next. These are model specific parameters. Go next. We are doing simulation type binary, does not matter. It will not be read because it's not used. And we will go here. Okay. So all of these parameters will be there. And we'll go ahead. And here we are using a temperature gradient in the simulation, as you will see here. Temperature gradient. So we are imposing directional solidification conditions where you are essentially imposing a temperature gradient across the solid liquid interface and translating it with a given velocity. Okay. This is precisely what you have in a Bridgman setup. Okay. In a Bridgman setup, you encourage crystals to grow in a given direction by imposing a temperature gradient at a given velocity, thereby imposing two things. You are imposing the thermal gradient and you are imposing the velocity of the solidification velocity. The thermal gradient sets the thermal length in the problem and the velocity sets the diffusion length in the problem. Okay, these two are the two important thermodynamic lengths in some sense, or macroscopic lengths, which determine the microscopic length scale in the problem. All right. So this is therefore an important thing to notice. This temperature gradient y, its details is something you can pick up by putting here. You will see that there is a way to establish what gradient you want to set in by specifying what is the delta T and that delta T in what distance is achieved. So that sets the gradient in the problem. Okay. And you can also specify the velocity. All right. Okay, very good. So the shift is off for some reason. Shift should be on, right? So you can put the shift on. What is the total distance? 400, right? So we will put it at 100. So everything else remains the same. And next. So here we have okay, so generate the in files. Required 10 component names, which I thought should be there. Oh, there are not 10 component names. Oh, we need to give one more. So just add nickel at the end. Okay.
Can we add it?
Huh?
Can we do some arbitrary?
Well, no. So it's important that you give the nickel because okay, here it can be arbitrary, but if you use the same column vector while you are extracting the thermodynamic information, it is important because it will establish the thermodynamic information in the same order in the CSV file. So whatever order you have here, it is important to have the same order in the code that generates the CSV file. Okay, so it is important to keep orders same. So it would not have generated files. So go back here to phases and compositions and open this number of components, change component name, and go to the last and input nickel. Just write nickel because one component name is missing. So it checks. No, sequence of names is something that you can choose. You can give arbitrary sequence of names. That is not important. But whatever sequence of names you give, there is a code to generate thermodynamic information from the pandat file or thermocal files. That same order of components has to be used in that code. What is it? What is the issue?
The last command there. Sometimes it's working and sometimes it isn't.
Wait, for whom it's not working?
Even now it's working. But it is not anything different to get it to work.
Yeah, so that is why, I mean, we have to be, for everybody else is working, no? Except for him.
No, I think it's not running it rather than.
Yeah. Path issue. Okay. Chirantan, it is a path issue. It was a path issue why it was not running. So it might be the same. उसका नहीं रन कर रहा? Okay, so let's go and run this now. Generate files first. How can you do all of that? Huh? Magic will not work in the software. Okay, so do run now. And you must see something happening. Taking too much time? Well, it is now solving for these many components. Yeah. So I mean, I'll quickly run it and just 40,000 steps, no? 40,000 steps, 1 hour. Okay, will not do that. Sure.
There is IM ceramic CPR.
So now you see here, you are solving for all of these components instead of 2 or 3 components as you would do in a real alloy, and you have 2 phases over here, and you are seeing the relative change of all of them, right? So you are doing a really multi-component system on your laptop. Okay. क्या डाउट है तुम लोगों का? नहीं उनका क्या डाउट है? ये कॉम्पोजिशन नहीं है, केमिकल पोटेंशियल है, एलिमेंट है। रनिंग फॉर एवरीबॉडी। थोड़ा सा लैपटॉप को उठा के रखो, गर्म हो जाएगा। Oh, hyphen. What is that? So NI you add it into the component list. It was missing, so that's what I showed them. You have to go to the phase component, end में nickel add करो. और इसमें nickel नहीं आएगा क्योंकि you only solve for 9 components. 10 में you only solve for the first 9, right? Independent. Is it running for all of you? Okay, we'll let the computer complain a little bit for some time so that we have generated some files, and this, as you see, takes time. So What is that?
Time stay because of reduction of time because we have to know like that.
Yeah, but we thought of it long and hard. We thought time would be more relevant for the experimentalist.
So now we have both steps and time.
He has added.
It's useful. We have to check whether it's yes. And all the inputs are currently marked as in graph. Now, if you want to look at the time step, you can't get the step information. Like in a large file, you have to go to. If it's in one line, it will be not visible properly here, but you can grab and find information fast.
So he added some modifications. Okay. So, in the interest of not paining the computer anymore, we will stop it at this point. Okay. I am stopping it at 3.26 e minus 6. Okay. That at least one file would have been written. Okay. So, very good. So go to the folder which you has just created. Oh, we stopped it before it ran anything. Nevertheless, it will take some time to run. Okay, so I will show you what it will give you. Arun has run this long enough. So I will show you what comes out. So you don't need to run your computer on your computer right now. Okay. Why does it not recognize, Arun? It doesn't recognize. All right, so I'll show you what the thing comes out to be. This one and it up. Okay, so guys, this is what you will get. This is how you would have the directional certification in the inside monitor alloy. All right, he did not put shift in his simulation. In your simulation that you did, you would have the shifting at 100. Okay.
Why do you have ions in the
It is just a materials property. If elasticity is on, then it will be used. But the material property is input. Okay, so here you will get the segregation of each of these components in the dendritic and interdendritic regions. And yeah, so this is all very useful for doing post analysis of what your heat treatment has to be and what phases could appear in these interdendritic regions. Right? You can do solidification path calculations of those compositions to figure out what goes on. What is that?
like kind of droplets?
Yes, those will appear. That typically happens in solidification. These are droplets. These are essentially films of liquid that get broken down into small droplets, and that happens due to in 2D they are happening due to just a breakup, but in 3D it happens due to Rayleigh instability.
So reason is very fast.
No, because it's solidifying, right? Finally, you will have entire thing solidifying, but the solid fraction is reducing as the temperature field is evolving. So this is the last liquid that is, its melting point is slightly different from the far fall liquid because of the segregation. Okay, so this is how you will get, right, if you run it completely with 40,000. And so there's a demonstration that you can do it, do a really real alloy, right, with all the thermodynamics inside, and in principle mobility is also inside. Okay, I'm not showing you an elasticity problem of a similar thing where we can do 10 components, but we have done it. We can do a stress applied coarsening simulation of, let's say, CMSX4. This is there in some of our presentations sometimes, so that also can be done. So you can simulate rafting, for example, in a real superalloy under heat treating conditions. So you put a stress and the system is at temperatures. All right. Okay, so one last example is what I will show is to do with elasticity and precipitation. So this is something that we will do quickly. So let's go back to our choice of infiles. So let's go back, import infile, and choose an infile over here from the file given to you. There's something called NILMO PPT, which is a short for NILMO precipitation. Okay, so this is a precipitate infile. We will do precipitation with this. Okay, select this, and there are multiple files. Okay, so which one do you want to choose? Huh? Multi PPT, not 3 variants. I also don't know, so you have to check. So it's complaining about something, so we'll leave that. So this is a very large simulation. Huh? So we can reduce it, doesn't really matter. 2000, it's 2000 cross 2000, so we'll make it 200 cross 200. So that is not really important. So we'll make it, I just want to check how many phases are there. The number of phases are 3, number of components are 3. Okay, and should be okay. Let's try it out. So we'll reduce it to 200 cross 200, and discretization is, as you see, we are doing precipitation now. So your length scale has reduced from something which was E-8, slightly sub-micron, to something which is nano, or really sub-nano. It is because the length scale of the microstructure has changed. All right, and this is what I've been impressing upon. Your length scale that you choose depends on the scale of the microstructure that you want to simulate. Right? It is small because that's what happens because of the, yes, because the interface width will be of the size of angstroms. All right, as you will see. Okay, this is a very long simulation. We will not do such a long simulation. We will do possibly the same thing that we have been doing. 20,000, 1,000, moving steps 10, next. Will not touch all of this. We can keep them all the same. Smoothing is just a Laplace correction. So here we will use the random cylinder and do what we were doing before. So 10.1, shielding distance 4, spread of 0.1. Okay. So we'll fill random cylinders with distribution. 10 is the average radius. A volume fraction is the total volume fraction of precipitates that you will be putting in. Shielding distance is minimum distance in grid point between two precipitates, and spread is essentially 10 plus minus some noise. So 10 plus minus 10%. So 10 plus 1, 10 minus 1. You will randomly distribute the precipitate.
It's a Gaussian distribution or
It's a Gaussian distribution. Okay, so with this, we will have the cylinder random coming in over here. And then we can go ahead and see what it simulates. So this is all okay. 3 values for tau. Why does it require 3 values for tau? It is because, where is the tau? Here, it requires 3 values for tau because there are 3 interfaces that are present. So presently we will just choose. So this is a long time we have not used this in file, but nevertheless. So this is function anisotropy 0. We will yes. So let's go there. It's a good thing that you asked. Material parameters. See, you are asking for 3 values. Okay, here I am putting it all the same, but you in principle can put all them different. Okay. So that I will tell you a little bit about little bit later. It is something to do with third phase absorption that you want to limit. Okay. No, this tau is not going to be used. It's just for this is going to be in a key that will be taken away in the next few releases. Okay, and so you are giving 100 Kelvin undercooling. The equilibrium temperature is 1200. You are giving 100 Kelvin. Generating files. We'll put over here, choose fuck, and then run. So it's a ternary alloy. You have two variants: gamma 1, gamma 2, and gamma. All right, and gamma is the matrix. All right, and as you see, there is only one variant that is surviving, gamma 1 variant. Remember when you did the filling, you did cylinder random, but that was of the only one phase you selected, alpha. You did fill up the second phase, so it doesn't appear in your calculation at all. All right. Next one, we will do the gamma 2. Gamma 2 will not come in the simulation at all because there's no nucleation. So unless you nucleate, it will not come. Okay. Only gamma 1. Gamma 2 is all 0 because nothing nucleated. Gamma is matrix. So you basically you nucleate the solid, the precipitate phase. Whatever is left out is filled by the matrix by default. Matrix. Domain change gamma. Domain filling. That is what. So I did not change here because you can fill gamma 1, gamma 2. Yes, you can fill gamma. If you want, let's say you can fill gamma as a gamma, even if you don't want to. Even if it get automatically filled in, you can specify to fill gamma. In principle, you can fill all sorts of all three phases that are existing. By default, gamma gets filled if it's empty, but you in the options it allows you to do. So as you see over here, because elasticity is getting solved, you are essentially slower than before for the same tunnel resolution. Okay? तुम लोग का चल रहा है? Okay, so can quickly check how many files have come in. We'll go here. So we are 13,000. So a few more files. So after this, there will be some classwork of creating the predicting system. I'll tell you how to do it. You'll go and do it yourself. All right? Attempt it. Yes, we'll create the infile. So you basically take the eutectic infile and modify it such that it becomes a predicting. Okay? I'll tell you how to do it. Why? You can stop the recording for the time being. Stop it, no?